On Tuesday, a 15-year-old boy in Magnolia, Texas, walked toward the edge of a flooded retention pond. It was an ordinary suburban basin, a graded culvert, a sheet of brown water that had risen quietly over a chain-link fence. He did not resurface. Crews searched and eventually recovered him 300 miles to the west in Bandera County, northwest of San Antonio. Another casualty of moving water on a road that looked, for one fatal second, like it could be crossed. To truly understand these tragedies, we must confront a profound spatial and temporal paradox. The system responsible for these deaths was not at that moment a hurricane. It was not even officially a tropical storm. Its peak sustained winds topped out at 45 miles per hour, a velocity weaker than a standard summer thunderstorm gust, an intensity you could survive standing in your own front yard. Yet, before it ever received a name, this meteorological anomaly had already exacted a lethal toll across Texas. This is the reality of Tropical Storm Arthur, which officially earned its name on June 17, 2026. Arriving before the Atlantic hurricane season was even 3 weeks old, it completely shattered the conventional calendar expectations of coastal communities. Climatologically, the Atlantic basin remains quiet in mid-June. The deep tropical engine of major hurricanes is not yet assembled. June systems are typically homegrown, minor nuisances. The National Hurricane Center explicitly designated this system as short-lived and weak. But here lies the systemic deception. While the public index for danger is almost entirely calibrated to wind speed, the actual architectural threat of this system was entirely hydraulic. The classification chased the catastrophe. It did not lead it. By the time Arthur was officially named, it had already spent days anchoring itself against an inland frontal boundary, operating as a slow-moving, massive engine of water. The metrics of this regional crisis are precise and documented. In central Texas, the atmospheric loading manifested as a historic deluge before any official tropical designation existed. Waco recorded nearly 3 inches of rainfall in a matter of hours. Camp Mabry in Austin shattered a daily rainfall record that had stood since 1964, forcing the closure of over 100 low-water crossings, triggering emergency evacuations of RV parks, and leaving drivers swept away in sudden currents. South of the border, the precursor system inflicted widespread structural damage across northeastern Mexico. In the state of Veracruz, more than a dozen municipalities reported severe flooding alongside dozens of destructive landslides. In Coahuila, over 5 inches of rain fell in a mere 2 hours, inundating the rivers of Piedras Negras and damaging up to 80% of the road infrastructure in a single municipality. This regional crisis exposes a fundamental breakdown of our protective barriers. We are witnessing a critical depletion of the landscape's natural storage capacity, where the infrastructure designed to mitigate seasonal variations is immediately overwhelmed by a systemic deficit in absorption time. To diagnose how a system too weak to overturn a patio umbrella can destabilize an entire geographical region, we must look beyond the standard metrics of wind categories. The true architecture of this crisis lies in an extraordinary and non-obvious geophysical convergence. Arthur did not originate as a clean textbook Atlantic storm. Days prior, its lineage began on the opposite side of the continent in the Pacific Ocean as a completely separate system named Tropical Storm Christina. Though Christina dissolved over the Pacific, its massive reservoir of tropical moisture did not vanish. It migrated northeast over Central America and emerged into the southern Gulf of Mexico. There, it collided with a westward-moving tropical wave tracking all the way from the coast of Africa. This messy, multi-oceanic collision stitched together a hybrid system that was completely saturated with water long before it ever developed an organized atmospheric structure. This brings us to a critical mechanical tipping point. When this moisture-heavy system pushed inland, it began interacting with a phenomenon known in geophysical literature as the brown ocean effect. Saturated, swampy, and waterlogged soils can mimic the thermal properties of a warm ocean, releasing heat and moisture to sustain a decaying storm. Arthur had spent days laying down its own fuel supply through precursor rains, priming the ground to keep its thermodynamic engine alive even as its wind fields collapsed. The conventional rules of atmospheric decay were inverted. The critical question that remains open, and the core mystery of this investigation, centers on the fatal disconnect between our instruments and reality. When the National Hurricane Center inevitably downgrades a waterlogged system to a post-tropical remnant and terminates its public advisories, does the danger truly evaporate? Or does the most lethal phase of a storm begin precisely when the world stops watching? To understand the answer, we must calculate the exact physics of forward momentum, the geometry of training rain bands, and the silent mechanics of compound flooding that are currently positioning themselves across the Deep South. To resolve this systemic paradox, we must deconstruct the primary operational variable that dictates the scale of a freshwater catastrophe. It is a deceptively simple physical law. Total rainfall accumulation at any specific point on the ground is a function of precipitation rate multiplied by the duration of the event. While a rapid tropical system traversing the landscape at 25 miles per hour sheds its water efficiently, allowing drainage infrastructure to cope, Arthur exhibited a critical reduction in forward momentum. Clenched by weak steering currents, the system crawled across the coast at a walking pace of approximately 9 miles per hour. This deceleration shifts the duration term in our equation to a catastrophic scale. A localized rainfall rate of 2 inches per hour ceases to be a manageable event when the clock runs continuously. For 2 hours, it represents a minor drainage strain. For 8 hours, it translates into 16 inches of water, transforming regional topographies into active flood zones. This mechanical slowdown triggers an even more destructive geometric phenomenon known in scientific literature as training. Much like rail cars passing sequentially over the exact same segment of track, individual rain bands line up and flow over identical watersheds for hours. This is not a single cloud losing its mass, but a highly organized assembly line of convective cells continuously generating upwind and discharging downwind. Under this geometric constraint, localized total accumulation decouples entirely from the official tracking map. A community located tens of miles from the technical center of the storm can receive a 20-inch bullseye, while an adjacent county receives a fraction of that amount. The placement of these catastrophic totals is dictated not by the classification of the storm, but by microscopic variables, the specific orientation of the bands, local terrain, and the accidental anchoring of frontal boundaries simultaneously. A secondary hydraulic layer activates at the coastal margin where the land meets the sea. This is the domain of storm surge, a bulk displacement of the sea surface, driven by the mechanical force of counterclockwise winds, physically piling ocean water against the coastline. Because of this rotational spin, the strongest push occurs consistently within the right front quadrant, east of the storm's landfall trajectory. For Arthur, this translated into a forecast surge of 2 to 4 feet stretching from Port Bolivar, Texas, eastward to Morgan City, Louisiana. In isolation, a 4-foot marine rise is modest, but when mapped onto a fractal coastline characterized by bays, bayous, low-lying peninsulas, and single-access highways, its structural impact is absolute. A 4-foot surge is sufficient to float vehicles and submerge evacuation routes, turning connected peninsulas into isolated islands before the freshwater deluge from the interior even arrives. When these two physical systems collide, they create a catastrophic phenomenon known as compound flooding. Under normal conditions, gravity drives fresh rainwater down regional gradients into the Gulf of Mexico. However, when storm surge raises the baseline sea level by 4 feet, the natural drainage mechanism fails. Seawater pushes inland, creating a hydraulic wall that forces local rivers and bayous to back up into coastal communities. This structural vulnerability is acutely realized in southern Louisiana, a landscape uniquely dependent on engineered pumping stations and levees. Large portions of this region sit at or below sea level, possessing almost no natural elevation gradient to shed water. When a slow-moving, water-heavy system forces these pumps to operate against both maximum capacity limits and an elevated marine boundary, the mathematics of the infrastructure simply collapse. The water has no outlet but lateral expansion through populated streets. This immediate physical threat forces an operational shift from advisory language to mandatory evacuation orders across multiple parishes. This decision-making process highlights the severe friction embedded within the human factor of emergency management. Local officials must issue high-stakes directives under conditions of absolute uncertainty, acting on probabilities before the heaviest rain bands materialize. This creates a dangerous psychological mismatch. While national news frames a 45-mile-per-hour storm as a minor nuisance, local authorities must convince residents to disrupt their lives and abandon property. This friction is compounded by the false alarm tax. When an aggressive warning is issued and a community is spared due to minor shifts in a rain band's path, public credibility is depleted. This creates a rational but dangerous conditioning effect, causing populations to ignore subsequent alerts, which directly increases mortality rates during later, more precise alignments of the hazard. This vulnerability is further exacerbated by online misinformation and superficial interpretations that consistently obscure the true mechanics of the crisis. Comment sections routinely invoke weather modification myths and abstract theories such as HAARP arrays to explain anomalous storm behavior. These narratives fall apart against the strict laws of energy budgets. A mature tropical system operates on a thermal energy scale that dwarfs the entire electrical generation capacity of human civilization by several orders of magnitude. There is no human technology capable of altering such a vast thermodynamic system. Conversely, dismissing the storm as media hype, based strictly on its low wind speed, ignores the fundamental reality that wind scales are entirely unrelated to water volume. Stripping away these false frames leaves us with the unglamorous, hard data. An ordinary early-season system carrying a maximized water payload, due to a profoundly altered thermodynamic baseline. To comprehend the raw thermodynamic capacity of this moisture machine, we must examine the physical engine driving the Gulf of Mexico itself. Arthur formed over water temperatures averaging 83.5 degrees Fahrenheit off the Texas coast, which translates to a profound expansion of the atmospheric gas tank. The fundamental physical law governing this mechanism is the Clausius-Clapeyron relationship, which dictates that for every single degree Celsius of atmospheric warming, the air can hold approximately 7% more water vapor. When mapped onto a basin running more than 1 full degree Celsius above its long-term baseline, this law ceases to be a theoretical abstraction. The atmosphere becomes heavily primed to carry and dump an elevated volume of water. Furthermore, rainfall extremes do not scale linearly with moisture. The internal dynamics of a slow-moving storm amplify this capacity, meaning that a generation ago, the exact same system under the exact same structural conditions would have possessed a much lower precipitation ceiling. This altered baseline is part of a structural regime change documented over the past 2 decades. In the middle of May, sea surface temperatures across the Gulf of Mexico tied all-time daily records, matching the exceptional warmth of 2024. Over the past 10 winters, the Gulf has averaged 0.8 of a degree Celsius above its long-term normal, a departure that quadrupled the deviation observed in the preceding 10-year block. This step change, linked by researchers to atmospheric shifts following the Super El Niño of 2015 and 2016, is reinforced by deep ocean currents like the Loop Current. which continuously pumps dense reservoirs of thermal energy northward through the Yucatan Channel. While seasonal outlooks for 2026 predicted a near-normal or below-normal total storm count due to El Niño-induced wind shear, this metric highlights a severe conceptual fault line in public perception. Storm count is merely a measure of frequency, telling us how many times the dice are rolled. Ocean heat content is a measure of loading, defining the catastrophic potential of a single roll. The historical blueprint for this specific water engine is written in the modern record of the Gulf Coast. In August of 2017, Hurricane Harvey demonstrated what happens when atmospheric steering currents collapse immediately after landfall. As its winds dropped rapidly below hurricane and tropical storm thresholds, the system stalled over southeastern Texas, converting into a pure hydrological machine. Harvey discharged over 60 inches of rainfall onto the flat coastal topography of the Houston metropolitan area. The sheer physical weight of this water pool was so immense that geophysicists recorded a measurable deformation of the Earth's crust, with the terrain sinking by as much as 2 centimeters under the trillions of gallons of water before recovering. The mortality toll and billions of dollars in structural damage occurred long after the cinematic violence of the wind had ceased, catching families in a quiet, rising trap within homes located entirely outside designated high-risk flood zones. An even more striking parallel to Arthur occurred in August of 2016 across southern Louisiana. That catastrophic event involved a system that never achieved hurricane status, never became a tropical storm, and never received an official name from the National Hurricane Center. It was simply an unnamed low-pressure mass of tropical moisture that stalled over a low-lying, pump-dependent landscape. It delivered over 20 inches of rainfall in a few days, destroying tens of thousands of homes and causing multiple fatalities without ever registering on the public index of named dangers. This historical baseline confirms the ultimate systemic lesson. The meteorological label is completely irrelevant to the physics of gravity and drainage. The water does not check for a name before breaching a barrier. As Arthur's core pushed toward the Texas-Louisiana border, the operational response split cleanly along this exact line of perception. In Texas, Governor Greg Abbott declared a state of emergency covering 101 counties, sizing the administrative response entirely to the water footprint rather than the 45-mile-per-hour wind headline. In Houston proper, aggressive preemptive engineering mitigated the worst-case scenario. Water managers deliberately pre-drained local reservoirs and drainage networks, lowering water levels in Lake Conroe and across Brazoria County to create structural capacity for the incoming deluge. This proactive measure allowed the urban core to escape catastrophic flooding, proving that targeted human intervention can alter the localized outcome of a disaster. Yet, this localized success introduces a final, highly dangerous cognitive trap as the remnant moisture continues its eastward trajectory. Tonight, as the National Hurricane Center issues its final advisory and reclassifies Arthur as a post-tropical cyclone, the public tracking graphics and warning cones will simply vanish from television broadcasts. To an untrained population in Mississippi, Alabama, and Georgia, the word weakening implies that the crisis has concluded. In reality, the structural degradation of the storm merely means the wind fields have unraveled. The sprawling moisture shield remains fully intact, advancing into a region recently hardened by a prolonged spring drought where baked soils repel rather than absorb immediate runoff. By removing the official name and the tracking center, the reclassification disarms the population at the exact moment the training rain bands pose their maximum inland threat. The system transitions into its most lethal phase precisely because it has decoupled from the track, moving silently downstream in time and space toward unwarned watersheds. This brings our systems analysis to its final, most critical coordinates, where the remaining atmospheric momentum collides with inland geography. As the sheared remnants of Arthur push deeper into the Interstate 10 corridor, the operational reality shifts toward a secondary, highly volatile hazard embedded within the decaying structure. While public attention remains fixated on the disappearing center, the sharp vertical contrast in wind speed and direction, known as low-level wind shear, intensifies dramatically. This mechanical twisting occurs as a cold front sliding southward out of Arkansas and Mississippi shears directly into the high-moisture air mass, feeding off the warm Gulf. The consequence is immediate. The sprawling rain bands begin to generate localized, rotating supercell thunderstorms. These are not the massive, highly visible tornadoes characteristic of the Great Plains, but small, rain-wrapped, nighttime spin-ups that materialize and dissipate in minutes. They are structurally impossible to detect visually and leave minimal lead time for radar warnings. Presenting an immediate threat to populations who assume a post-tropical low is incapable of tornadic violence. This localized violence underpins the speculative upper boundary of our risk model. The worst plausible case, where all physical variables align to maximize destruction. In this scenario, the forward speed of this post-tropical remnant drops to near zero as it catches on a stationary boundary over a dense population corridor. The atmospheric gas tank, continuously recharged by the 83-degree waters of the Gulf, continues to pump moisture into a localized zone that lacks the pre-drained reservoir systems of major metropolitan areas. The result is a severe, widespread flash flood event that rapidly transitions into a regional infrastructure failure. Small, unregulated creeks and urban drainage networks overflow their physical limits, inundating roads and trapping residents within structures that have no historical record of flooding. This ceiling demonstrates that a structurally unraveled storm can achieve local lethality that rivals a major hurricane. Purely through the persistence of its water payload, the defense against this decentralized threat relies entirely on proactive public administration, as demonstrated in New Orleans by Mayor Helena Moreno. Confronting a system that national headlines consistently minimized as a 45-mile-per-hour nuisance, city officials refuse to participate in the public error of reading a wind scale as a general danger metric. Emergency crews aggressively pre-positioned rescue boats, deployed barricades across historically vulnerable streets, and opened sandbag distribution centers before the core moisture shield ever reached southeastern Louisiana. This tactical response frames the decaying system not as an existential apocalypse, but as a critical stress test of municipal infrastructure and emergency muscle memory. It recognizes that preserving administrative credibility through cautious underwarning is a fatal strategy when dealing with the probabilistic physics of water. Ultimately, the documented history of modern tropical systems confirms that the traditional mental model of hurricane hazards is fundamentally obsolete. For decades, historical data on United States tropical fatalities has revealed an unmistakable shift in where and how people die. The classic cinematic image of coastal populations overwhelmed by a wall of wind and storm surge at the beach has been mathematically overtaken by a quieter inland reality. The vast majority of modern fatalities stem directly from freshwater drowning, occurring miles from the coastline and days after the initial landfall event. People die in their vehicles on ordinary roads or are trapped in their homes after the storm has been officially downgraded and retired from the news cycle. The hazard has migrated upstream in time and space. While the public's perception remains anchored to the coast and the categorization scale, the tragic outcomes in Magnolia and Bandera County stand as permanent structural markers of this cognitive gap. The 15-year-old boy who stepped toward the edge of a suburban retention pond and the driver swept away by a few feet of water on a routine road were both victims of a system that lacked a menacing category or a terrifying name. They were undone by the patient, relentless nature of water, moving through an overloaded system. As the remnants of Arthur dissolve into the wider atmospheric circulation of the Deep South over the next 48 hours, the true measure of the event will not be found in its peak wind velocity or its short lifespan on a tracking map. It will be written in the absolute limits of our infrastructure, the precision of our emergency protocols, and our collective willingness to respect the physics of a waterlogged storm long after the wind has gone silent. This brings us to the final, sobering resolution of our systems analysis, where the mathematical and physical limits of our coastal and inland defenses are laid bare. Throughout this investigation, we have tracked the transformation of an ordinary, low-wind atmospheric disturbance into a highly lethal hydrological engine. We have seen how a 45-mile-per-hour system, structurally unraveled by wind shear and stripped of its official identity, can systematically overwhelm geographic regions, bypass infrastructural safeguards, and claim human lives. This outcome is not an accident of nature, but the predictable consequence of a rigid societal dependence on categorical labels that fail to map on to the physical reality of water. When we evaluate the macro-ecological footprint of Tropical Storm Arthur across the Deep South, the true boundary of the crisis is found not in the air, but on the saturated ground where human engineering attempts to dictate the behavior of gravity. The systemic failure points exposed by this event reveal a dangerous structural mismatch between the design criteria of our infrastructure and the change-in thermodynamic state of the Gulf Basin. As established by the Clausius-Clapeyron relationship, an ocean running more than a full degree Celsius above its historical baseline forces the atmosphere to operate with an expanded moisture capacity, scaling up the potential intensity of localized downpours. Our drainage networks, culverts, pumping stations, and retention basins were engineered using historical averages that assume a stable climate baseline. When a slow-moving, multi-oceanic moisture mass like Arthur parks over these systems, it delivers a volume of water that simply exceeds the volumetric ceiling of the machinery. The resulting backup is a matter of pure physics. The pumps in southern Louisiana cannot move water faster than their maximum mechanical rating, and when the sea surface is simultaneously elevated by storm surge, the mathematical equation governing regional drainage simply defaults to zero. This operational collapse highlights the severe limits of human control over macro-environmental systems, thoroughly deconstructing the superficial narratives that populate public discourse. The impulse to view an anomalous event through the lens of weaponized weather modification, or to dismiss it entirely as media hype, stems from the same cognitive flaw: a profound inability to comprehend the sheer scale of natural energy budgets. Human civilization operates within narrow structural boundaries, while a single moisture-loaded storm, drawing fuel from an elevated ocean heat content, handles kinetic and thermal energies that dwarf our entire global output. We cannot engineer these systems away, nor can we safely ignore them because they lack a high category number on a wind scale. The only effective defense is structural mitigation, proactive public administration, and an absolute grounding in the logic of hard physical limits. The pre-draining protocols executed in Houston and the aggressive pre-positioning of resources in New Orleans demonstrate that human intervention can successfully alter the localized path of a disaster. By lowering reservoir levels and preparing infrastructure before the peak rainfall arrived, water managers proved that systemic foresight can mitigate the human toll. However, these local successes also illuminate a deeper structural inequality embedded within our geographical defenses. For every major metropolitan area equipped with post-Harvey engineering protocols and extensive reservoir systems, there are dozens of rural counties and small towns with no such protections. When the geometry of slow steering currents and training rain bands drops a 20-inch bullseye on an unmanaged, drought-baked watershed, the human factor is left entirely exposed. The damage decouples from the official track, hitting the places where no national news cameras are watching, and where residents have no historical precedent to guide their survival instincts. The final, inescapable lesson of Tropical Storm Arthur is that our traditional metrics for assessing environmental peril are dangerously obsolete. The fatalities in Magnolia and Bandera County were not caused by a Category 5 monster, but by a system that by the wind metric was barely a storm at all. They occurred because our collective safety model remains anchored to a wind scale, confusing a measure of one specific hazard for a measure of total systemic danger. As the remnant moisture of this event finally dissipates into the wider Atlantic circulation, it leaves behind a clear and urgent diagnostic warning. A warming Gulf means that the ceiling on freshwater flooding has permanently risen, while our psychological and engineered barriers remain fixed. If we continue to allow bureaucratic classifications and wind headlines to dictate our level of fear, we will remain completely defenseless against the patient, relentless